So thank you very much for that nice introduction, and I also thank the organizers for organizing the Club de la Balanza. It's a great honor to be here today and speak about the new generation of Kibble balances. Next slide, please. So on May 20th, 2019, so a little bit over a year ago, the international prototype of the kilogram, the IPK, was dethroned as the ultimate mass standard. And instead, we put this, what's called the Planck constant, on the throne, and all mass measurements throughout the world will eventually go back to Planck's constant. I say will eventually, because as you shall see in the next slide, please, that this will be a gradual process. So we not just turn the switch on May 20th and everything goes back to H. No, no, no. What will happen is, and you see this here kind of depicted in a mathematical way, there will be a linear combination. We have some of the old measurement, which relates back to the IPK, this is shown at the top, some alpha, some fraction, and then some fraction relates back to H. And then we add this linear combination and we have a mass standard. So this will be all done in phases. So you see down at the graph here, you see times at the beginning, alpha is 1, so we only have the flat and medium prototype, and then alpha slowly goes down, and eventually we will be in a state where all mass realizations will go back to H. So when will we make these changes? Well, these changes will be made whenever the CCM meets, and there is a new data from what's called a key comparison, and we have more trust in our system to measure masses. So next slide, please. I can explain this a little bit more. So the change will basically occur in 3 phases. Here on the table, I show 4 phases, because phase 0 is already the phase that we left behind. So for a very long time, from 1889 to about 2019, this was only the mass of the international prototype of the kilogram, IPK, that gave us the mass. It was defined to be 1 kilogram and had 0 uncertainty. And then going forward from May 1st up to now, basically, we still have the IPK, but now it has a 10 microgram uncertainty. Where does this uncertainty come from? Well, we use the IPK, the international community used the IPK to measure Planck's constant. And the way we could measure Planck's constant, the uncertainty was about 10 parts per billion. And that uncertainty is now, because Planck's constant has been fixed, so the uncertainty has to go somewhere else, and it went into kilogram. So this is what we are doing right now. We have still, the mass of the kilogram is 1 kilogram, but it has an uncertainty of 10 microgram. And this will happen until date 1. So when will date 1 be? It could be possibly next year when the CCM meets, and then we will have a consensus value, and I will show you in the next slide how this consensus value is obtained. The consensus value comes out of 3 things, and you will see that. And we will have more and more consensus values until we are really happy with the process. And then in day 2, we just rely on a fixed value of H. And each country that has a Kibble balance or a silicon sphere can use their own H value to disseminate mass. So the next slide, please. So this is how the first consensus value will be calculated. So there will be 3 things that go into it, 3 ingredients. One will be the international prototype of the kilogram. This is where the value that we have. One will be the data from the pilot study. So the pilot study was the study where H was determined before the redefinition. And then what's called the KCRV, it's the key comparison reference value from the key comparison. So the key comparison was something that happened earlier in the year, and several NMIs, and I'll show you a slide, have measured with their Planck balances or their silicon sphere a mass, and these masses have been compared. And so all these 3 ingredients will go in, and each one will be a third. So they will be just weighed by a third. And this is why you see that the kilogram will still have a little bit influence in this. At the next consensus value, there will be another key comparison and the data from the previous consensus value from this one. So slowly after time, the influence of the kilogram will go down and the influence of the H will go up. So next slide, please. So this is the data from the key comparison that was carried out in basically 2019, 2020. You see here we have 5 Kibble balances that submitted values. This is the BIPM, the CRIS, NIM in China, NIST, and NRC in Canada. And then we have 2 values that were obtained by using the X-ray crystal density method. This is the silicon sphere method, and this is NMIJ and PPD. And you see the data agrees really well. If you would draw these data points of 2 sigma uncertainties, then they overlap. This is a plot of 1 sigma uncertainty, so they're not quite overlapping. But of course, as you know, if you have 3 data points, you expect 1 to be outside 1 sigma. So here we have 7 data points. So having 2 outside 1 sigma isn't that big of a deal. So the data set's very consistent. You see this green line is the key comparison reference value, and the uncertainty of the key comparison reference value is 7.5 micrograms. So it's already lower than the last time when we measured H, where we had an uncertainty of about 10 ppb or 10 micrograms. So I think we're in really good shape. What the redefinition means, the world and so far has been very consistent, and the database is getting better and better. So I think this goes for promises, as good promise for the future. So let me briefly explain these 2 methods, this X-ray crystal density method and also the Kibble method, which are these primary realizations of the unit of mass at the kilogram level. Next slide, please. So you see here on the left side, you see a photo of one of the silicon spheres out of silicon-28. It's pretty large, it's about 100 millimeter in diameter. And on the right side, you see the Kibble balance that we have at NIST. It's also very large. It's about 2 meters and 20 or so tall, and is in a vacuum vessel that is 180 meters in diameter. Next slide, please. So there's these 2 ways to connect Planck constant to the kilogram, and I will briefly explain to you. So here I just explain the fundamental big ideas, and then later on I explain a little bit more the technical way of doing it. In the X-ray crystal density method, which is here shown on the left, you start out by using a small mass. The small mass that we know very well is the mass of the electron. And the mass of the electron, we know, depends on Rydberg's constant. So this is a constant that you get when you measure the spectrum of the hydrogen atom. And in there is H. So the mass of the electron is known, can be related back to H. It has a small uncertainty, but the uncertainty is very small. It's less than 50. And then we have to scale this mass of the electron up into a kilogram. And for those who remember how heavy an electron is, it's about 9.1 times 10 to the minus 31 kilograms. So you need to scale that mass up by 30 orders of magnitude. And how do you do this? Well, this is done in multiple stages, and this is shown here in the last equation where I say the mass of a kilogram is little n times the Avogadro constant times r times n. Let's start out with the little r. The little r just compares the mass of an electron to the mass of a silicon atom. This is an atomic physics experiment that can be done in a trap very well. And once you have a silicon atom, then you can use Avogadro's constant, and I will show this to you in the next slides, to scale it up by having a mole worth of silicon atoms, which would be 28 grams. And then you need the little n, which scales up from 28 grams to 1 kilogram. So this is one way. The other way has to do with quantum electrical standards. This is what's called the Kibble balance and was formerly called the Watt balance. So Kibble invented that in 1974, and it was called Watt balance at first, and then Kibble passed away in 2014. We renamed it to Kibble balance to honor his invention. In a way, it works. It goes back to 2 quantum electrical standards. One is the von Klitzing constant, which is shown here on the left. Rk is h over e squared. And this is the quantum Hall effect. If you have a 2-dimensional electron gas in a very cold substrate like gallium arsenide, then the Hall resistance is quantized in this very convenient way, which is about 25.8 kilo ohms h over e squared. That was discovered in the 1980s. In 1962, Brian Josephson invented the Josephson effect, or discovered the Josephson effect, theoretically. And that is when you have a sandwich out of a superconductor, a non-conducting material, and another superconductor, and you shine a microwave into it, you get the voltage that's given by 2e over h times the microwave frequency. And this h over 2e, which is this inverse of what I just said, is the Josephson constant. So what you can do now is you can measure electrical power by combining resistance measurement and voltage measurement. Okay? Everybody knows that electric power is V times I, and if I write I as V over R, V divided by R, I can write this as V squared divided by R, which is exactly what I write here. So I have the Josephson constant squared divided by the Josephson constant gives me H over 4. So the Kibble balance, what it does is now it compares electrical power to mechanical power. Mechanical power is given by the weight and the velocity, and electrical power is given by voltage times current, which is traceable to the quantum electrical standards. So let me show you a little more how this works in a technical fashion. Let's go to the next slide. So how do you count large numbers? And this is kind of a scheme that shows you how this is done. So if you want to figure out how many Coke bottles are in the stack shown on the left, one thing you can do is you can measure the length, big L, the height, big H, the width, capital W, of that stack, and then divide it by the volume of a unit cell. So this would be one crate of these Coke bottles, which is given by little w, little l, and lowercase h. So you can figure out the number of bottles by just having the microscopic volume divided by the microscopic volumes times the number of bottles. So you don't need to count anything, you just measure lengths. Okay, next slide, please. Well, it is very inconvenient to measure something that is a box, like this stack of Coke bottles that we have seen, because a perfect box doesn't have sharp corner, there's always little chamfers and so forth. It's much easier to measure a sphere. So people in Germany, Australia, Japan, National Avogadro collaboration have made a perfect silicon sphere. And that sphere is perfectly round, so there's no corners. So you only need to measure one dimension to get the microscopic volume, and that dimension is the diameter. And this is shown on the left picture. You can put the sphere in one of these interferometers and you can measure this diameter. In order to measure the microscopic volume, well, silicon is a perfect crystal. It has a lattice constant, and you can measure the lattice constant with X-ray crystallography. So you build an interferometer, you basically move one of these lamellas, and you measure the motion of the lamella with an optical interferometer, and you see fringes in the optical interferometer as the intensity of the X-ray intensity changes periodically as you move this lamella. So you can figure out the volume of a unit cell, which is given by, if you just have a perfect cube, it would be A0 to the third power. But with the way the crystal is cut, you measure actually a diagonal in the cube, which is given by D2 to 0, so you get another root 2 times 16. So you can now measure the number of atoms by just taking the equation that we did before. We divide the microscopic volume divided by the microscopic volumes, and everybody knows 4/3 r to the 3 power pi is the microscopic volume of a sphere. You divide this by the microscopic value, and then you need to know that in a silicon single crystal cell, there's about 8 atoms per unit cell, so you can figure out how many atoms there are. And one thing that I want to say here, if you look at the final equation, you see the number of atoms is here just a number, pi divided by 12 divided by 2. Then you have this ratio. This ratio measures d, which is the diameter of the sphere, divided by the length of a unit cell to the third power. And you see the whole equation makes sense because on the left side, the number doesn't have a unit, and the right side is also unitless. Because you divide two lengths by each other, so the length meter drops out. So you think that this is a very easy measurement, but in reality, it's actually very hard, and it shows us how good the system of units is, how well our measurement system works. I'll show this to you in the next slide, please. The interesting thing is these two Ds that I showed you are measured at very different scales and also different places. So the little D that's on the top, which is the diameter of the sphere, which is about 10 centimeters, as I said before, is measured in Japan and in Germany. And the D2 to 0, which is this length of the unit cell, is measured in Italy with this X-ray interferometer. And the size of that is 2 times 10 to the minus 10 meters. And yet, when you make this ratio, you can measure this to about 5 parts in 10 to the 8. And that is totally astounding. You can see the SI is really for all times, for all people, right? I mean, the people in Germany and Japan measure one, people in Italy measure the other, and you combine it, and it has super small uncertainties. Everything drops out. 2 very different scales. I mean, this is, I think, an amazing proof how well our system fields works. This is really amazing. All right, let's go to the next slide, and I'll show you how the Kibble balance works. So in the Kibble balance, you have 2 modes. One is called the force mode, and the other one is called the velocity mode. I will show this to you in a brief video after this, but I want to briefly show you the most important components here, and also the equations. So what we have is we have this big wheel on the top, which looks like a snowflake, and that is a balancing mechanism. On the balancing mechanism, all the balancing happens on the left side. So on the right side, you only have a tera mass. That is always the same. So what happens is once you put the mass on the left side, you get this downward force, mg, and the downward force is now counteracted by an electromagnetic force. That is given by I times B times L. So I is the current that runs in a coil that's inside a magnet. B is the magnetic flux density. So in our case, it's about 0.5 Tesla. And L is the length of the wire. So IBL gives us the force. We can measure I very well. We can measure G very well. So the only thing that's difficult to measure is BL. And in order to measure BL, this is the stroke of genius that Brian Kibble had. We use this velocity mode. We use the very same coil that you had seen before, and we drive it through the magnetic field by moving it up and down. And as you move the coil up and down in the magnetic field, you get an induced voltage, U. And that induced voltage is proportional to V times BL. So by just measuring the voltage and the velocity, you can figure out BL. You see this also here on the equation. If you solve both equations for BL, then you can get rid of the BL. You make them equal. You have on the left side mg divided by I, and on the right side U divided by V. You multiply it out, and you see mgv is ui. So this means mechanical power on the left side is the electrical power on the right side. And if you pay attention to the color, you see in the last equation that the force mg is green and the velocity is orange. And also on the right side, u is orange and I is green. That means of that product ui, one factor is measured in velocity mode, the other factor is measured in force mode. So this is only virtual power, it's not real power. That means a lot of friction and losses don't matter because this product only exists in a computer and it's a perfect product. Okay, let me show you a bunch of videos so you see this how this works. Next slide, please. So this just shows you the setup that we have. So we have this balance wheel. We have on the right side a little motor that allows us to move the wheel. We have on the left side the mass pan and the coil in the magnetic field. Next slide, please. But in reality, it's a little bit more complicated because if you just have a coil in an open room, it will be like a big antenna. It will see all the 50 hertz, 60 hertz that you have from computers and other consumers. So in order to make this work, we have to surround this stuff by iron. The iron also has the advantage that it guides the magnetic flux directly where the magnet wire is, where the coil is. So that makes the system efficient, but also provides shielding. Next slide, please. So this slide, I show you the force mode. So we can zoom in here now. You see how the wheel can move on the top. What happens is now we have here an interferometer that measures the position of the coil. And once you put the mass on, the coil will go down. And then we turn on the current, and it brings the system up such that our balance is again horizontal. We have a null detector that detects our null of the balance. And then we know F is IPL. So let's look at it again. Mass goes on, wheel moves. The interferometer detects the motion. We energize the coil with electrical current. The coil lifts it up. I have now the static equilibrium, so the force is IPL. Okay, next slide, please. And this is now the velocity mode. So in velocity mode, we move the coil up and down with a constant velocity. In our case, the velocity is about 1 millimeter per second. And as you can see, when the coil moves down, here we get a negative induced voltage that's proportional to the velocity. Then the bottom stops. When it goes up, we get a positive voltage in the voltmeter. So here we get the voltage is the velocity times BL, and we can use that mode to calculate BL. Next slide, please. So this is how, in principle, the Kibble balance works. So what I want to tell you now is these new, smaller Kibble balances. That has a big advantage. So previously, we have used the kilogram to define mass. The kilogram defined it only at one fixed point. Yeah? And that is very similar to the system that we had for the meter. So on the left side, I have a plot that showed how the redefinition of the meter came along. And you see here in the lower plot, you see how well people could measure the meter, and you see how well people could measure the speed of light. And at some point in the 80s, 1980, people could measure the speed of light better than they could measure the meter. And then people say, okay, let's redefine the meter into the distance that light travels in 1/300 millionth of a second. Next slide, please. And that made it possible to measure now the distance to the moon. The same relative uncertainty, we can measure the scale on a chip. Next slide, please. And now we're going to do this also with the kilogram. So here you see a very similar plot that shows the progress that we made measuring the Planck constant to measuring mass. And you see the Planck constant is almost as good as the mass. And I just told you that in the latest key comparison, we could measure to 7.5 or so microgram. Next slide, please. So now we can also do the same thing that the people in the meter did, can do the same thing with the kilogram. So if you look here, this is the CMC, the calibration and measurement capabilities for the US. This is how well the US can calibrate masses. And I show you the scale from 100 gram to 3 kilograms. This is the traditional way that we used to do before the redefinition. Next slide, please. And this is how well the NIST Kibble balance can do. So one Kibble balance can roughly accommodate a factor of 20. So the big Kibble balance that we have, NIST 4, can measure from 100 gram to 2 kilograms. And we can do better than traditional mass metrology, as you can see here. So at 1 kilogram, we're just slightly better, but at 100 gram, we're actually better by a lot, almost factor 2. Next slide. So now let's zoom out. So this is the calibration and measurement capabilities from 1 milligram to 1 kilogram. So where else can we bring this technology to? Next slide, please. So at very low scales, we have what's called an EFB, an electrostatic force balance. Gordon Shaw has been pioneering this, and you can measure masses that are smaller than 100 micrograms, and you can measure masses up to 10 milligrams with this technology. Next slide. So the intermediate range, and this is what I want to talk about in the remainder of the talk, we have now built a tabletop balance that measures in air, that works in the 1 to 10 gram. It's not quite as good as the CMC, but it's definitely as good as the E2 mass. And then we're building right now QEMs, and we don't have results yet, so this is just dashed, this is just projected, where we hope to measure from about 5 grams to 100 grams. This is factor 20 again. Next slide, please. So this is our tabletop watt balance. This has been built by Leon Chow. It has a range from 1 gram to 10 gram and a relative uncertainty of about 10 to the minus 6. And it's about 30 centimeters in diameter and 30 centimeters tall. Next slide, please. So here's the uncertainty budget of the skip G1, as we like to call it. So 1 gram, we can measure with a relative uncertainty of 6.3 times 10 to the minus 6. 5 grams, we can measure with a relative uncertainty of 1.8 times 10 to the minus 6. The reason we can measure larger masses more precisely is because we have a force problem. So there's a constant force that we cannot get rid of that makes an uncertainty, and the larger the mass is, the smaller the contribution will be. You see this here in this little pie chart. The force part of the pie chart gets much larger for 1 gram. Next slide, please. There's efforts in other countries, and I just want to touch this very shortly. I don't think I have a whole lot more time left here. There's efforts at PTB that is building a system that can go from 1 milligram to 1 kilogram. They're using a commercial weighing cell, and this is called the Planck Balance 1, PD1. You see it here on the left side on the table. And you need a whole rack of electronics and an air bath for the resistor. Next slide, please. So here you see a picture of this weighing cell, and they put a second voice coil on there so they can move it. Interesting feature of this experiment is that the velocity mode is done in a dynamic mode, so the coil is vibrated up and down. Next slide, please. Another effort is going on at NPL. NPL uses a vertical design. CNAM is also looking into a vertical seismometer design for a tabletop kibble balance. They're using commercial watt meters, but they hope to use a self-built watt meter eventually. Next slide. I want to show you our last ideas. This 100-gram kibble balance at NIST. We call these the QEMS, the Quantum Electrical Mechanical Metrology Suite. And the idea is that the quantum Hall standard are becoming smaller and smaller and smaller. So we have now a tabletop quantum graphene resistor, and there's also a cryo-cooled programmable chosen voltage system that we can just put in a rack. It's very small, and the idea is to have a whole NMI in one room. We have the kibble balance, the resistor, and the voltmeter. So both are quantum devices in one room. So we started the design and construction, and we hope to be done next year. And this machine will have a measurement uncertainty of smaller than 2 micrograms for masses smaller than 100 grams. And I can show you already some stuff that we got. So next slide, please. So this is the idea. We're still discussing the balance mechanism. We are not sure if we do beam balance or a flexor strip design, but here you see the system. It's much, much smaller than the big NIST 4 balance. It will only be about 1 meter or so in diameter and 1 meter tall. And next slide. What we have already designed and we've already gotten is the magnet system. So the magnet system is about 110 kilograms heavy. So it's a factor 8 or so lighter than the one that we use for NIST 4. And I have a picture for you also in the next slide where you can see how small it is. Slide, please. Can I have the next slide? Oh, yeah. Here you see the magnet, and we measured the flatness of the field. So the yellow line on the right is after the magnet has been ground. The other lines are the first measurements, so it wasn't perfect at the beginning, but we ground it down to make it very, very flat. And you see how small the magnet is. It's just the weight that's still heavy because it's a lot of iron. It's 110 kilograms, but you see the size of the hand. It's a relatively small magnet. It has a very similar shape and design as the NIST 4 magnet. Okay, let me summarize these different watt balances and electrostatic balance that we have at NIST right now. I have one slide that gives you an overview of this. Next slide, please. So we have the electrostatic balance, and we hope to extend the mass range from 1 milligram to 500 milligram. It actually goes well below 1 milligram, but this is for 1 milligram to 1 kilogram kind of purposes. There's a publication by Gordon Shaw. We are working on KIP-G2, which is the next iteration of KIP-G1. We have the prototype that I showed you to measure 1 gram and 5 gram with uncertainties of about 9 microgram. We are currently building the QEMS, quantum electrical mechanical measurement suite, and then we have NIST 4, which is our research grade instrument that they can measure from 100 grams to 2 kilograms. Next slide, please. So recently, we've also looked into using the Kibble principle to build a torque calibrator. The whole Kibble principle also works in a rotating reference frame. In this case, the induced voltage is proportional to the angular velocity and this PL factor. And then if you put current in the coil, you get a torque. So the idea that you see here on the left, we have a D-shaped coil that's in between a permanent magnet system, and we can use that to measure induced generate torques. Next slide. So we have two different systems that we investigate for this. We have one where the magnetization is perpendicular and one where the magnetization is parallel to the rotation axis. So now I have the last slide, please. So what we're trying to do is build a system that can measure 1 Newton meter torque with an uncertainty of 0.1%. And this is currently ongoing under design, and hopefully we have a device that can do that at the end of next year. So you see there's lots of going on. It's very exciting times to be in wire balances. And if you show me the next slide, you see the whole team. So obviously all the stuff I'm not doing alone. I have a great team of people that I'm working with. Next slide, please. And this is the team that works here. Leon Chow on the left, Dave Newell, our group leader, Rafael Marangoni, who is working in Krems, but he unfortunately left NIST, myself, Frank Seifert, Sean Pratt, and Doreen Haddad. And in the middle, you see a little model that we built of our NIST 4 Kibble balance, which is a factor 2 smaller. Yeah, thank you very much for your attention.